There might have been an entire cosmos before the Big Bang. Physics offers concrete models, and some are testable today. Imagine a sky that stretches backward without an edge. A pre-Big Bang model extends spacetime before t equals 0. That matters because singularities vanish and predictions become testable. Quantum gravity can smooth infinities, replacing them with a bounce. Alternately, emergent physics can create time from deeper microstates. Loop quantum cosmology predicts a contracting phase, then a bounce. Simulations show maximal energy densities staying finite, not infinite. So before the Big Bang can be physically meaningful. Different models classify how before connects with our universe. This matters because connectivity changes observable predictions like wave spectra. A close view shows a dense core, and we see local causal structure. A pre-Big Bang model defines whether time continues or emerges anew. Bounce models reverse contraction into expansion through quantum pressure. Emergent models instead generate time from timeless microscopic degrees of freedom. The ekpyrotic idea uses colliding higher-dimensional branes to create hot expansion. That predicts specific non-Gaussian fingerprints in primordial fluctuations, so classification changes what signatures we should look for. A cosmic clock ticks backward across a contracting era, then forward. Understanding these behaviors matters because they shape primordial signals we observe. Structural shells and streams reveal how modes propagate across phases. Contracting phases amplify certain quantum modes, changing wave spectra. Emergent scenarios instead damp modes, producing smoother initial conditions. Cyclic models repeat expansion and crunch phases across cosmological cycles. The ekpyrotic picture can produce a very flat spectrum with unique signatures. A bounce can tilt gravitational waves toward higher frequencies. That shift would appear as a blue tilt in cosmic backgrounds. So how before behaves directly changes observable predictions. Light from the universe's baby years carries subtle, fossilized clues. These clues matter because they let us falsify pre-Big Bang ideas. Filamentary structures trace how early perturbations stretched and evolved. Quantum fluctuations during a bounce seed distinct density patterns. Phase transitions, or collisions, introduce localized hotspots and asymmetries. Primordial gravitational waves can carry spectral tilts from contracting phases. CMB polarization maps can reveal tiny B-mode patterns from primordial waves. Detection of a blue gravitational wave tilt would strongly support contracting models. So the sky holds testable records of potential pre-Big Bang eras. Instruments are precise ears listening to the universe's faint hum. Better instruments matter because they can turn theory into evidence. Measurement scenes show detectors and delicate readouts scanning the sky. Gravitational wave detectors search broad frequency bands for stochastic backgrounds. CMB satellites map polarization to exquisite sensitivities, revealing faint imprints. Large galaxy surveys trace primordial seeds into today's structure. LiteBIRD plans to measure polarization down to nanokelvin levels. Pulsar timing arrays aim to detect nanohertz gravitational backgrounds over decades. So instruments translate faint cosmic whispers into testable data. Theories are frameworks that extend known physics backward in time. Choosing the right framework matters because predictions depend on starting rules. Debris-like fragments of math hint at different fundamental assumptions. String cosmology invokes extra dimensions and dynamical branes to start universes. Loop quantum gravity quantizes spacetime, removing singular infinities through discreteness. Asymptotic safety seeks a high-energy fixed point for gravity's equations. In loop models, curvature peaks at a finite maximum, not infinity. String pre-Big Bang phases can last orders of magnitude longer than Planck times. So theoretical rules shape which pre-Big Bang picture arises. A vast horizon appears where empirical science meets deep metaphysics. This matters because only falsifiable ideas can be tested and refined. A wide vista suggests the limits of what data can decide. Falsifiability needs concrete predictions that observations could contradict. Robustness arises when different frameworks predict the same signature. Null results narrow theory space, guiding better models over time. A measured blue tilt would favor contracting cosmologies over emergent ones. If no signal appears, constraints push models towards subtler mechanisms. So philosophical clarity helps keep speculations scientifically useful. We started by asking if a cosmos existed before the Big Bang. If you like this, subscribe for more thoughtful cosmic deep dives. So physics lets us imagine and sometimes test a before.